BocaPhysics series on electromagnetism. In today's lecture, I'm going to discuss inductance. Over the previous few lectures, we've talked about motional EMF, Faraday's law, the Flux rule. So I'm going to begin today with a set of circuits. Determine what the magnetic flux is through the ith circuit. And we'll put an I subscript to indicate that we are talking about the ith circuit. So that's due to the flux from all the other circuits. And notice here when I've added up the contributions from each of the circuits, I did not exclude the contribution from the ith circuit itself. Okay, so all these carry current, and therefore they give rise to magnetic fields, and hence we figure out, well, if I integrate over this area here, loop I, then I can determine the magnetic flux to everything, including itself. So if I happen to have changing current in any of these, that means that's going to give rise to a changing flux and hence to an EMF. So this is just the flux rule. Minus summation from j equals 1 to n. Of the time derivative of the magnetic flux through the ith loop due to the jth circuit. We're going to look at this term more closely. I can rewrite this as the derivative of the magnetic flux with respect to the current that flows through the J circuit times the time derivative of the current flowing through the J circuit. Okay, so this quantity here, Mij, is the mutual inductance. And it represents the coupling between circuits. If J happens to be equal to I, then I have the mutual inductance of an ith circuit with respect to itself. So a better way of saying that is this is actually the self-inductance, and that is denoted by the capital letter L. And what that represents is that there's a changing circuit that changes opposed. Okay? There's a useful expression, and it's called Neumann's formula, and I will derive that next. just want to consider the coupling between two circuits, circuit 1 and circuit 2. We want to know what the mutual inductance is. So to that end, I'm going to calculate the flux through circuit 2 due to the magnetic field of circuit 1. Well, the flux is just the surface integral of the magnetic field. In this case, again, it's a magnetic field due to circuit 1 through circuit 2. Incorporating the Biot-Savart law, and I'll convert this into a simpler looking integral. This is in fact equal to the curl with respect to the subscript 2 coordinates. Of the line integral around circuit 1 over one of the magnitudes of the separation vector. Okay. I can use another operation. You can actually make use of Stokes' theorem. To convert this outside surface integral to a line integral. And it's the mutual inductance I'm after. So that's just the flux through circuit 2 due to circuit 1 divided by the current carried by circuit 1. And that'll just be equal to mu naught over 4 pi C2, C1 the dot product of dl1 and dl2 over the magnitude of the separation vector. Now, a couple points I want to make. Remember I said that mutual inductance between two circuits is the derivative of the flux with respect to the current flowing through the other circuit. Okay? If you happen to be dealing with steady, rigid circuits, and also we'll add the condition that it has to be in a linear medium, then this just goes over to magnetic flux divided by the current. Okay, so you've got steady, rigid, or not steady currents, sorry, but rigid stationary circuits. then I can replace the derivative with V over I. Okay? Another feature that I'm going to point out here, notice there's no dependence on I. So this really just is a function of the geometry of the system. And in that sense, it's analogous to the capacitor. The capacitor was a function of the geometry of the system when you're talking about the charges building up on the plates and so forth, and in that you figure out what the potential was if you knew the geometry of it, which was described by the capacitance. Here we're describing the inductance, in this case mutual inductance, and also self-inductance is in the geometry of the system. Another important point to notice here is that it's symmetric with respect to the circuits. Now, if you first consider two circular loops, that might not seem like such a big deal, but mutual inductance, whether you calculate the magnetic field due to this loop and determine the flux to this one and then divide by I, or vice versa, the mutual inductance is the same. That's really a remarkable result. So therefore, Mij is equal to Mji. So that means that you've got two ways of solving these kinds of problems, and usually, unless you're glutton for punishment, you always want to choose the easier way. Okay? So that is Neumann's formula for the mutual inductance between two circuits. I'm now going to go ahead and work through a number of examples. Calculating mutual inductance. For only one of them, we're actually going to use Neumann's formula. For the others, we'll just calculate the magnetic fields and the fluxes, not worry about putting it into this form, except for the last problem we'll go through. Okay? The first example that I'm going to consider is that of a solenoid, a long straight solenoid. Determine what is its self-inductance. So in other words, I need to figure out what the magnetic flux is. So to begin, we need to figure out, well, what's the magnetic field? Well, if you get a long straight solenoid, it's just uniform inside and vanishes outside. By the way, I'm just going to draw this so that the z-axis stays pointing to the right. Okay? So this is inside and 0 outside. The flux through one loop it's just going to be equal to the magnetic field times cross-sectional area. Well, the magnetic field is uniform, so this is just magnetic field times area. It's just mu naught n I times A. And of course, n is the number of turns per unit length. times capital letter N over little L. Okay, but I don't need to just know what the self-inductance is through a single loop. I need to know through all N loops. So therefore, through N loops, or what's the same thing, little n times L loops. Magnetic flux is equal to mu naught N squared, little n squared, times L times A, where I is current and A is the cross-sectional area. To determine the inductance, well, since we are dealing with a rigid stationary circuit, self-inductance is just phi over I, or mu naught N squared L A. So once again, the inductance is a function solely of the geometry of the system in question. Now let's suppose that we've got two solenoids. And they're coaxial. But one is very long, and one is of length Li. So here's a very long outside solenoid. Imagine it goes off the board in both directions. And then we've got our smaller solenoid on the inside. And I want to determine what is the mutual inductance between these two solenoids. Now, remember what I said about mutual inductance. It's symmetric. So I've got a choice here. I can figure out, well, assuming that the inside cylinder had, or solenoid rather, gave rise to a certain magnetic field, I determine what the flux is. But as it turns out, it's actually a much easier problem if I figure out what the magnetic field is due to the outside cylinder, the outer cylinder, because in that case, for the very long outer cylinder, the magnetic field is just equal to mu naught times the number of turns per unit length in the outside cylinder times I. And therefore, to figure out the flux, let's suppose these have radii Ri and Ro respectively. So Ri is the inner radius of inner cylinder, and Ro is the radius of the outer cylinder. So therefore, the flux through one of the loops of the inner cylinder is just mu naught N naught I times the cross-sectional area, times the cross-sectional area of the inner cylinder, which is just pi Ri squared. Okay? But we don't need to know just the flux through only one loop. We need to figure out the flux through the whole solenoid. So through Ni loops, or Ni times length, it's going to be equal to not, in the number of turns per unit length of the outside cylinder, number of turns per unit length of the inside cylinder times the length of the inside cylinder times I times pi r I squared. Okay, and to figure out what the mutual inductance is, well, that's just V over I. And there's your answer. Again, if you attempted it in the opposite direction, well, you have an idea of how complicated that would be. If you watch the videos of calculating the magnetic field due to cylinders using the Biot formula, so really gets ugly fast. Okay. So we looked at two cylinders. Let's take a look at a transformer now. Simple transformers are comprised of primary coil and a secondary coil. And we'll assume that they're very tightly wrapped. Basically around each other. Derive the transformer equation. And again, my lack of artistic talent fails me here, but anyway, they're wrapped around each other. So if there is a changing magnetic flux, there will be an EMF induced. Flux through primary coil. If it's composed of N turns, or N sub P turns. There's a change in the flux, and that's going to be the case in all N turns of the primary coil. It's going to induce an EMF in the primary coil. In similar fashion, secondary coil is composed of NS turns times change in flux with respect to time. So the change in the flux is the same, okay? But because you've got more turns in one set of coils as opposed to other, you can actually step up and step down voltages. So therefore, because these are the same, that tells me that E of P over NP is equal to ES over NS. And sometimes it's written like this. EMF of the primary over the EMF of the secondary is equal to number of turns primary and number of turns secondary. So there's your transformer equation. Okay? Now let's consider the self-inductance of a toroid. And we'll treat one that has a rectangular cross-section. Make the inner radius A, the outer radius B, and the height H. So the first order of business is to know what is the magnetic field. Well, we calculated this before using Ampere's law during an earlier lecture, and that's just equal to mu naught times Ni over 2 pi s in a circumferential direction, where capital N is the number of turns. I want to figure out what the magnetic flux is through one of those loops. Circumferential means it's just going around in a circle into and out of the board. And since we are looking at the cross-sectional area of this slice right here, we're seeing the loop just lies in the plane of the board. In the plane, the magnetic field is pointing in the same direction as normal. So we'll integrate from 0 to h, going up and down, and also from A to B, going from here to here. And the magnetic field inside is equal to N mu naught I over 2 pi s ds. And doing the integration, you'll see that that's equal to mu naught N I over 2 pi times h natural log of B over A. Okay? So that's the flux through a single loop. We need to figure out what the flux is through n loops. So they're n loops, so it's just n times the flux through a single loop. So through n loops, I wind up with mu n squared times I over 2 pi h natural log of B over A. It's the self-inductance that we're after, so again, rigid stationary circuit, that's just equal to phi over I, which is just mu naught n squared over 2 pi h natural log of B over A. Only this time we're going to calculate the mutual inductance. And mutual inductance to a long straight wire. And a rectangular loop. Again, we'll assume this loop has height h, and we'll assume that the distance from the wire to the left-hand side of the loop is just A, and from the wire to the right-hand side of the loop is B. And I'm going to figure out, well, what's the mutual inductance this time. Instead of self-inductance. And with mutual inductance, you always have choice. You calculate the magnetic field into this loop, And you can envision this basically as a giant loop, other sides of which are very, very far away. Turns out, of course, it's much easier just to figure out, well, what's the magnetic field due to the long straight wire, and write that down immediately. Is equal to mu naught I over 2 pi s, and once again, any circumferential direction. So just right-hand rule, the thumb goes in the direction of the current, your fingers curl around in the direction of the magnetic field. So if you want to figure out what the flux is through the loop, and this time there's only one loop to worry about. So we integrate from 0 to h in the z direction, and from A to B in the radial direction. It's the mutual inductance we're concerned with, and again, as I said, it doesn't matter which way you choose it, but this, as far as the actual physics goes, or the final result goes, I should say, but as far as the amount of time and effort you have to expend, there are some ways that are much easier, and we chose an easier way. Mutual inductance is just the magnetic flux divided by the current, so that's mu naught h 2 pi over 2 pi natural log of b over a, and notice the similarities between these two expressions. The form is nearly identical, only we've got a factor of n squared here, reflecting the fact that you've got n turns, and over here you just have a single loop, okay? And that, of course, arises from the similarity in parts of the magnetic field due to a toroid and due to a long straight wire, and also the geometry that we chose. Okay? The next example I'm going to work through is that of calculating the mutual inductance between a long straight wire and a circular loop. Okay, so this problem is going to take a little bit more effort than the previous one. We'll assume once again that it's the wire that's carrying the current for the sake of calculating the inductance, and then calculate the flux through the circular loop. If we did it in reverse, you'd have to worry about elliptic integrals of this. The next example I'm going to work through is that of the mutual inductance between a long straight wire and a circular loop. Just as in the previous example, I'm going to calculate the magnetic field due to the long straight wire and figure out what the flux is through the loop. So this is equal to mu naught I over 2 pi s, again in the circumferential direction. I'm going to assume that the distance from the wire to the center of the circle is b, and that the radius of the circle is A. Okay, so I'm going to point out relation between how Z and S and A are all related to each other. So therefore, the equation of the circle in this case is A squared is equal to Z squared plus S minus B squared. And therefore, Z is equal to plus or minus square root of A squared minus S minus B squared. Okay? In this case, I'm going to do the dz integration first. So I have mu naught I over 2 pi s. And again, circumferential direction means it's pointing into the board, and that's the normal of our loop. Here we're going to integrate from 0 to square root of A squared minus S minus B squared. And I'm going to take a factor of 2 here because actually we're just going to be integrating basically the upper half of the loop. So you can do that if you take in a factor of 2. So which way, where does S extend? Well, so in that case, it means we're going to pick our limits from B plus A to B minus A. Okay? And I will have one more integral to solve. It's going to be mu naught I over pi, integral from B plus A to B minus A, ds of square root of A squared minus S minus B squared over S. Now, this is not an intractable problem, it's solvable. It's just that it means you're probably going to have to look up some integrals and tables. So when I get to this point, I always like to look in my grad sheet in Reisig, and that tells me that this integral is equal to square root of A squared minus S minus B squared, evaluated from B minus A, or B plus A to B minus A, plus A squared minus B squared, B plus A minus A of ds over S, A squared minus S minus B squared, and then the last term, 2b over 2, B plus A, B minus A, ds over square root of A squared minus S minus B squared, close brackets. Okay. So this first integral, or this first term, goes to 0 when I evaluate it at the limits, and then you see you've got another couple of integrals that need to be involved, calculated. So again, you can solve Green's chain rising. By the way, going from this step to this step is 2.267 in Gradstein and Reisig. That's page 84 in my edition. First term becomes first non-vanishing term, B squared minus A squared, sine inverse squared minus b squared plus 2bs over s square root of 4b squared minus b sine inverse of minus 2s plus 2b over square root of 4a squared. And again, that's evaluated from b plus a to b minus a. By the way, this is, again, graduating and rising to get from this integral to here. You'll get 2.266, again, it's page 84. And to get from this integral to this one, again, graduating and rising, 2.261, page 81. Okay, so I'm going to go ahead and skip over a few steps. Mu naught over I over pi. So we've got mu naught I over pi, square root of b squared minus a squared. We're evaluating at b plus a to b minus a, so that'll be sine inverse of 1 minus sine inverse of minus 1. Over here, this is sine of minus 1 minus sine inverse again of 1. So sine of 1, inverse of 1, that's just equal to pi over 2. And this is equal to 3 pi over 2. This is 3 pi over 2. And this is equal to pi over 2. So in each of these cases, you're taking the difference between 3 pi over 2 and pi over 2, which is just going to be pi. Notice these signs are going to be reversed here. You'll get a pi from this one and from this one, which cancels out the pi in the denominator. And this will be positive, and this term will be negative. So you wind up with mu naught I times b minus square root of b squared minus a squared. Now, it's a mutual inductance we're after. So again, rigid stationary circuits and otherwise linear media. Basically, we've been doing all these problems in vacuum. So this is just equal to mu naught b minus square root of b squared minus a squared. And there's your answer. Now, it might have looked almost intractable or a real hassle. Isn't so bad if you use the table of integrals. If you're glutton for punishment, I suppose you can just go ahead and do the math, all the math yourself, but I prefer to take a shortcut. Okay, so that's mutual inductance. Now, before we contrasted the case of a toroid with a rectangular cross-section with a long straight wire and a rectangular loop, and we pointed out how similar in form the two inductances were. In one case, we were calculating self-inductance, in the other case, mutual inductance. Here we're looking at mutual inductance. Now, let's suppose that you had a toroid of circular cross-section. So can you write down self-inductance right away? Well, what's different here? Well, you've only got one loop. Over here you've got n loops. So therefore, self-inductance, I can write down immediately, is just mu naught n squared times b minus square root of b squared minus a squared, close parentheses. And there's your answer. I'll just leave it up there for a minute or so. And we've got one more problem to work today, and this time we will make use of Neumann's formula, or the Neumann formula. The last problem I'm going to consider is that of two coaxial circular loops, and I'm going to determine the mutual inductance between them. Mutual inductance using Neumann's formula is just mu naught over 4 pi, line integral around circuit 1, line integral around circuit 2, dl1 dot dl2 over r2 minus r1. It doesn't really matter what order you do it in. We'll suppose that these are a distance z apart. Now there are a bunch of different ways you can solve this problem or treat it. Sometimes you might be told, well, you've got a couple of loops and they're very far away. In that case, you can make use of the dipole approximation to write down a simplified expression for the magnetic field due to the loop. In this case, at this stage, I'm not going to do that quite yet. So what are R1 and R2 equal to? Well, R1 is just A cosine phi1 in the x direction plus A sine phi1 in the y direction. And we'll assume that that's sitting in the xy plane, so therefore z is equal to 0 there. R2, however, is sitting at distance z above. First one's going to be A cosine phi1 in the x direction plus A sine phi1 y direction. Second, R2 is B cosine phi2 in the x direction plus B sine phi2 in the y direction plus Z in the z direction. And therefore, dl1 is equal to minus A sine phi1 d phi1 x direction plus A cosine phi1 d phi1 y direction, and dl2 is equal to minus B sine phi1 d phi1 x direction plus B sine phi, oops, I'm sorry, there should be 2's down there. So it's sine phi2 d phi2 plus B sine phi2 d phi2 y direction, and the z term integrates to 0 in that case. Okay, so what's dl1 dotted into dl2? Well, it'll have AB times cosine phi1 cosine phi2 don't want to write it like that. Let's do AB sine phi1 sine phi2 plus cosine phi1 cosine phi2, and each of those terms has factors of d phi1 and d phi2. Well, I can simplify that expression, and that's just equal to AB times cosine phi1 minus phi2 d phi1 d phi2. Okay, so what's 1 over magnitude of the separation vector in this case? over the square root of a cosine phi 1 minus b cosine phi 2 squared plus a sine phi 1 minus b sine phi 2 all squared plus z squared. So I won't write out all the intermediate steps, but you see you'll get an a squared cosine squared phi 1 and an a squared sine squared phi 1. So you make use of that trigonometric identity that cosine squared plus sine squared, the same argument, is just equal to 1. So we'll just wind up with a squared, wind up with b squared, and then we got our z squared. But then we'll also have the cross terms, and that'll have this form. You'll have sine phi 1 sine phi 2 plus cosine phi 1 cosine phi 2. Oh, and you get a minus sign out front. So that's minus 2ab over cosine phi 1 minus phi 2. Just trying to save myself a little space on the board here. Okay, so if I make a substitution of variables to make this a little bit neater, let's say we'll call k equal to ab over a squared plus b squared plus z squared. Now, substitute these back into my original formula. I can pull an AB out front. And then I can also pull this term out from the denominator as well. So mutual inductance, it can be written as mu naught AB over 4 pi square root of AB over K, where K is defined as AB over A squared plus B squared plus Z squared. And we're doing 2 line integrals around each of the loops. You have cosine phi 1 minus phi 2 on the numerator, and then we have 1 over square root of 1 minus 1 over the square root of 1 minus 2K cosine phi 1 minus phi 2. I can actually work this problem a little bit more. Eliminate one of the integrals. So unfortunately, I'm going to have to erase this on the left-hand side. And I'll make a change of variables here. Let's say we want to integrate phi 1 first. Okay. It's convenient to make a change of variables. We'll say u is equal to phi 1 minus phi 2. And we're integrating around loops, so that means we're integrating from 0 to 2 pi in both cases. But turns out we are integrating over a complete cycle. We are integrating from 0 to 2 pi after all. So why not just change the limits here? Go from 0 to 2 pi here. We're integrating over du, and hence we'll go from 0 to 2 pi when we're integrating over d phi 2, of course. So that's just going to give me 2 pi, and I'll be left with mu naught over 2 square root of k ab times the integral of 0 to 2 pi cosine u du over 1 minus 2k cosine u. And there's your answer. If you're feeling really ambitious, you can go ahead and write this in terms of the complete elliptic integrals k and e. If you're not feeling so ambitious, just leave it like this. It is instructed, however, to consider what happens if the circuits are far apart. So in other words, what if z is much, much larger than either a or b? So the distance between them is great. I can make use of the binomial theorem and expand this denominator. And I have to erase this right-hand side, unfortunately, again. This is just equal to 1 plus k. Okay, so I can plug this back into here. So mutual inductance is now mu naught over 2 square root of k ab. 0 to 2 pi. We've got the cosine u in the numerator still, so it's cosine u times 1 plus k cosine u du. The first term is going to integrate to 0. Why? You take the integral of cosine u, that's going to give you a sine u, and integral of sine u or cosine it from 0 to 2 pi is just 0. So that'll just leave the second term. That is just going to be equal to k times pi. And there's your answer. If we assume that the distance between the circuits is much larger than the dimensions of the circuits themselves. Now, I also mentioned you can also make the dipole approximation. If one of the other loops is very small. And in that case, your magnetic field due to a magnetic dipole is just mu naught m over 4 pi r cubed 2 cosine theta in the radial direction plus sine theta in the theta direction. Of course, remember that the magnetic dipole moment for a circular loop is just going to be I times pi times the radius of the loop squared. Okay? So that is using Neumann's formula to figure out what the inductance is due to 2 coaxial circular loops.